Press your thumb against this screen right now. Actually do it. Feel that? Those tiny ridges. Pressing into the glass. You've had that exact pattern since before you were born, and here's the part that should genuinely bother you. Nobody, not a single scientist on Earth, can tell you with certainty why it's there. We know fingerprints exist. We know they're unique. We know they've solved crimes and unlocked a billion iPhones. What we don't fully know is why evolution bothered giving us tiny mountain ranges on our fingertips in the first place. You'd think something this useful for identifying criminals would have an obvious primary purpose. It doesn't. The forensic use is a total accident, a side effect nobody was planning for 100,000 years ago. So let's actually dig into what these ridges are doing, why every single one of them is different, and why some of the leading explanations sound less like biology and more like a superhero origin story. Let's start with the basics, because most people have no idea how fingerprints actually form. You are not born with a random pattern stamped onto you like a barcode. Your fingerprint pattern develops while you're still in the womb, somewhere between weeks 13 and 19 of pregnancy. During this window, the deepest layer of your skin, called the basal layer, grows faster than the layers around it, since it's sandwiched between other layers that aren't growing at the same rate. It has nowhere to go but buckle. It literally folds and wrinkles under pressure, the exact same way a too large bedsheet bunches up when you shove it into a smaller box. Those folds become permanent ridges, and once they're set, they don't change for the rest of your life, aside from getting bigger as you grow. Here's the detail that makes this genuinely wild. Identical twins, who share basically the same genetic code, do not have identical fingerprints. Why? Because the exact pattern of folding depends on tiny, random variables in the womb. The precise pressure of amniotic, exact position of your finger against the womb wall, microscopic differences in blood flow and skin growth rate down to the millimeter. Your fingerprints aren't purely genetic. They're the result of a one-time biological accident happening in a slightly different way for every single person who has ever existed, which is why, out of the roughly 108 billion humans who have ever lived, no two sets of fingerprints have ever matched. Not once. Not even close. Okay, so we know how they form. Now here's where things get genuinely uncertain, because there are three major competing theories about why humans evolved these ridges at all, and scientists still argue about which one, or which combination, is correct. Theory 1, grip. This is the one most people assume is obviously true, and for a while, it was the leading explanation. The idea is that ridges increase friction, the same logic behind tire treads on a car. More surface texture means more grip on rough or wet surfaces, which would have been useful for climbing trees, grasping branches, and handling tools. It's a clean, intuitive explanation. There's just one problem. When researchers actually tested this in labs, using devices that measured the friction of ridged versus smooth artificial fingertip material, the results were messy. In some conditions, ridges actually reduce the total contact area with a flat surface, which should, in theory, reduce friction, not increase it. Grip almost certainly plays some role, but it's not the clean slam dunk explanation everyone assumed for decades. Theory 2, touch sensitivity. This one's less intuitive, but has surprisingly strong evidence behind it. Your fingertips are packed with pressure-sensing nerve endings, and researchers have found that the ridges actually amplify vibrations when your finger moves across a textured surface. Think of it like a phonograph needle running across the grooves of a vinyl record. The ridges convert fine surface texture into vibration patterns that get funneled directly to specific touch receptors underneath the skin, essentially turning your fingertip into a natural amplifier for detecting texture. Studies using robotic fingertips built with and without ridges found that the ridged versions were dramatically better at detecting fine texture differences. This suggests fingerprints might exist less for gripping objects and more for reading them, letting you distinguish a rough surface from a smooth one or wet from dry with far more precision than smooth skin ever could. Theory 3, and this one sounds almost too strange to be real, protection through channeling water. Some researchers have proposed that ridges function like a drainage system, channeling sweat, and water away from the contact point of your fingertip. The theory is that this would help maintain consistent grip in wet conditions by preventing a thin water film from building up between your finger and whatever you're touching, similar to the grooves cut into car tires that channel water away to prevent hydroplaning. It's a compelling analogy, though it's the least tested of the three theories and remains more speculative than the sensory amplification research. The honest, slightly unsatisfying truth is that fingerprints probably aren't the result of one single evolutionary pressure. They're likely a combination of enhanced touch sensitivity, some grip benefit in certain conditions, and possibly better water management, all bundled into one structure that evolution kept around because, on balance, it helped more than it hurt. Now here's where this connects back to something ancient, because fingerprints aren't just a human thing. Other primates have them. Koalas, of all animals, have fingerprints so similar to human ones that forensic experts have genuinely mixed up koala prints with human prints at crime scenes, which is either hilarious or deeply unsettling, depending on your mood. The fact that fingerprints show up independently across such different branches of the animal family tree, primates and marsupials evolving separately for tens of millions of years, is a strong signal that these ridges are solving a real, recurring problem. Nature doesn't usually reinvent the same complicated structure from scratch in unrelated species unless that structure is doing something genuinely useful. For early humans specifically, that usefulness would have mattered enormously. Precision grip on stone tools while knapping a blade, feeling the exact texture of a plant to determine if it's safe to eat before your eyes even confirm it, sensing subtle changes in bark or vine texture while climbing. In a world with no labels, no safety instructions, and no way to Google weather something was dangerous, your fingertips were doing real diagnostic work every single day, feeding your brain a constant stream of texture data that could mean the difference between a solid handhold and a fatal fall. And this is the part that should change how you think about something you've never once consciously appreciated. Every time you pick up a coffee cup, feel for your phone in a dark room, or run your thumb along a stitch in your shirt to see if it's coming loose, you're using a piece of biological engineering that took shape before you were even born, refined across millions of years across multiple species. Also that a tiny patch of skin on your fingertip could tell your brain more about the world than your eyes sometimes can. So the next time you press your thumb against a screen, or leave a print on a glass, or get asked to press your finger onto a scanner at the airport, remember that you're not just leaving evidence of where you've been. You're carrying around a piece of unresolved scientific mystery, quietly stamped onto the tips of your fingers, doing its job so well you've never once had to think about it.